In the last class, we discussed about electric potential because of a point charge. Today, we talk about a dipole. So if you have a dipole and you want to find what is the electric potential at any point in space, then what should be the approach? Let's see. So for dipole, we know certain things. We know that a dipole means you should have a negative charge, right? Suppose I take a negative Q and there's a distance, a separation, and we have exactly equal in terms of magnitude another charge which is positive. So one is negative and the other is positive, and the distance is fixed. The distance always remains fixed. This kind of configuration is known as an electric dipole. So two opposite nature of exactly equal in magnitude is separated by a distance, fixed distance, and we take in, suppose 2a is the fixed distance, and somewhere in the middle we locate here exact midpoint, and let us call this midpoint as O, such that this distance of positive charge is a and the distance from negative charge is also a. So this is the midpoint. This configuration is known as an electric dipole. It constitutes a dipole. There's one very important quantity associated with dipole, and that's known as dipole moment. And we know its dipole moment is a vector quantity, so we'll indicate it here. And this dipole moment is from negative to positive. It's a vector quantity, and this is equal to, the magnitude of this is equal to 2aq, the magnitude of the charge and the distance between. So the product of this times the charge that's there. So this constitutes the magnitude of the dipole moment, and we denote this by P as in general notation. Now, having this in picture, we are going to now modify our diagram, and we'll now figure out, if suppose this is any arbitrary point P, a point of interest, at P we want to find the potential. We want to find the potential. Okay, so what we need to do, and this P, I'm just rubbing this off here, just need to do a bit of modification. So we know these things, so I'm just rubbing this here, and this P from O is at a distance R from O. So we'll join this. Suppose we join this here like this, and suppose this distance is R, and the angle, the orientation is also generalized. It's in the generalized form, and suppose that orientation is making an angle theta degrees with this axis. This is the axial position along the axis of the line which is connecting these two charges. So it makes theta degrees here. This is all we know, and we are interested in to find what is the electrostatic potential. Whatever we have learnt about the potential, we'll apply that concept here. Now let's point certain positions here. So suppose this Q, I mark it A and I mark it B. So what exactly we know? We know that potential at a point due to a point charge, what's required is the distance of this charge from this point where we want to find the electric potential. That is required, and also the magnitude of the charge is required. Okay, that's all we know. We want to find. So let's see, if we have this configuration, what strategy can we apply? Suppose I make a construction and I extend this line somewhere here, and I drop a perpendicular from this point A, suppose this point A, I drop a perpendicular on this line, this line. So I'll make this O, this is P, suppose this is A, B, C, suppose this is C, and I drop from A a perpendicular on C after projecting it backwards. Okay, let's do this construction. And from B So make it point B here. From B, we'll again drop a perpendicular on this line, which is connecting the point O and P, and this we mark as 90 degrees. So this is what we make a construction, and we know that this is A, right? So we know this is A. So if this is the construction that we have made, this geometrical construction, this AO is actually in this triangle is the hypotenuse. Why? Because this is opposite to the perpendicular, the angle 90 degrees. So with this geometry, we'll proceed further and then we'll complete this triangle here. So we'll join this point, these 2 points that we are interested in, and also we'll join these 2 points here to make a construction. So this is how we make a construction, and these are straight lines, so make it straight. These are straight lines. So that we make a triangle, and let us make dotted lines here so as not to confuse. Okay. Well, this is how we make the construction. And now we'll try to check what more can be done. Well, if you look carefully in this triangle ACP and triangle P, suppose I indicate this point where we drop a perpendicular from point B on this line which is OP. This point is D. So this is R and this is D and this is B. Well, okay, now in triangle ACP, look carefully, and triangle PDB, this is what the configuration looks like. So if this angle is theta in this triangle, this angle is theta, this angle will also be theta. Why? It's vertically opposite angles. Okay. Now for a short dipole, we know for a short dipole, and we assume every time this short dipole, we know that R should be very much greater than A. So this A and A, which is 2A, the distance between is very much less as compared to R. So we are taking a generalized position. R is very much large in magnitude wise as compared to the distance from the midpoint on the line which is connecting these 2 charges of the dipole. So having here in this way, in this part of the geometry, we'll try to figure out, can we get this expression here in terms of R and A, because we are interested in PA and PB in the equation. We are interested in the equation, this distance PA and this distance PB. That's what we are interested in. So if we make this assumption that R is very much greater than A, so can we write that if we tend to make this larger, don't you think that this PA eventually, so this is going to somewhat shrink over here, and this PA would become OP, right? PA. So if this is shrinking, this would become, this distance would become PC. The PC is going to, sorry, not PO, PC is going to become this, the same as PA if R is very much greater than A. So this A is going to shrink. As it shrinks, we imagine this is going to get longer. So somewhat this distance is going to be PC. So if this is in triangle this, so we can, in triangle APC, we can assume that this, if this is the condition, this PA that we are interested in would become PC. And this implies that, what is PC? This PC is OP plus OC. Okay, so this PC, which implies that PA, this implies that PA is equal to OP plus OC. Now look carefully in this small triangle. If this is theta, what is this OC? So this is base, right? And this is hypotenuse. So OC over A is cos theta. So therefore OC is equal to A cos theta. So we can write this OP. We already know this is R. So therefore from here we can write PA is equal to R plus A cos theta. A cos theta. Okay, now look here similarly in this part of the construction. Look here. Similarly, if this holds true that R is very much greater than A that we have assumed, then don't you think that this PD, this PD would eventually become PB? Why? Because if this would shrink, this would lie again somewhat near to the O. As A shrinks, assume that to be very much smaller as compared to R, this DB eventually would tend to OB, which would make this PD equals PB. So here we got PA equals this. So also if this holds true, we can write this PB, which will come in this equation. This PB should be becoming this, this PB would become PD. So we can write PB should become PD, which implies that this PD is equal to OP minus OD. So we can write this PD is equal to OP minus OD. Now in this triangle, small triangle, if you look carefully, this is hypotenuse. If you take cos theta, right? If you take cos theta, so cos theta is going to be this base, which is OD divided by A. So therefore this OD becomes A cos theta. So we can write therefore PD is equal to PB. Therefore PB should be equal to R minus, right? So since this OD is OP minus OD. So OP is R minus OD, which is A cos theta. So these two equations we have here, that's going to help us in figuring it out. What is the potential at V? So potential at V, if you want to write the potential at this should be equal to superposition sum of this plus this. So this should be equal to the potential because of this point charge and the potential because of this point charge. So potential because of this point charge is going to be this, which is 1 over 4 pi epsilon naught, right? And if you take this Q divided by, suppose we take this first, this is minus Q divided by, what is this distance, which is PA? We know this PA is R plus A cos theta. Okay, this plus potential because of this charge is going to be 1 over 4 pi epsilon naught. It will be Q divided by PB, right? So this is PB and PB is R plus minus A cos theta. This is what we get. All right, so if you take common Q and Q divided by 4 pi epsilon naught and you put that in bracket, we get V potential VP should be equal to Q over 4 pi epsilon naught. Here you would write 1 over R minus A cos theta minus 1 over R plus A cos theta. Now it's just the mathematical manipulations and simplifications. So if you take the LCM in the bracket, so we get here Vp is equal to Q over 4 pi epsilon naught. So this comes out to be R plus A cos theta minus R plus A. So if you put it here, it will be minus R, minus and minus would become plus. So it becomes A cos theta over a minus b times a plus b, so it could be written r square minus a square cos square theta. This is what we get. So we see this r and r gets cancelled, and we are getting a cos theta and a cos theta, which is 2a cos theta in the numerator, and in the denominator we get r square minus a square cos square theta. Okay, so let us write this expression here. So we are getting Vp finally as q over 4 pi epsilon naught. So we'll write it q over 4 pi epsilon naught. And in the bracket, we are r and gar get cancelled. So we are getting 2a cos theta divided by r square minus a square cos square theta. This is what we get. Now look carefully, this 2a and q, this 2a and q is the magnitude of dipole moment. So we can substitute that. So we can just modify and simplify this in terms of this. So potential at P we are getting q over 4 pi epsilon naught 2aq, we can write it 2aq. So it becomes times P cos theta over here. It becomes r square minus a square cos square theta. This is what we get as the net potential because of the electric dipole. Well, now we can have three conditions. If we want this P to align with the axis, so then theta is going to be 0. If theta goes 0 here, which means that cos 0 is going to be 1, and here also cos theta would become 1. So we'll be left with three situations. So take note of these steps, and then we'll talk about the three situations. We'll take this P to any arbitrary point here, r, with the same r, we'll take somewhere on the axis, and here we'll again take on this negative axis, and then we'll find if it is on perpendicular equatorial, what's going to be. So with this general equation, we can derive the results for the three situations. So take down these steps, and then we'll move forward. Okay, so I'm rubbing this part of the board. So we get this here. So if point P lies on the axial line towards positive x-axis, suppose. Okay, so then theta equals 0. Okay, if this is the situation, then what's going to be the net potential? It's going to be 1 over 4 pi epsilon naught. We would, in the numerator, we would put this cos theta, which is 0. So cos 0 is 1, so it's just P. In the numerator, it becomes r square minus a square. This is what we get when we have theta is equal to 0. So this is first situation. So now we take this situation. If we take this theta degrees to be 180, so the angle is 180, which means that if this point lies on the axial line but on the negative side of the x-axis, if this is a situation, theta is going to become 180 degrees. So if you put in this value here, so cos theta, cos 180 is going to become minus 1, and here also it becomes minus 1 squared. So we get Vp, which is the electric potential, this electric potential here, on the negative x-axis, we'll be getting, it will be minus, so let's take out the negative out, so it will be minus 1 over 4 pi epsilon naught, and this would become P divided by R squared minus, it's A squared, and cos 180 is minus 1, squared, it would be again 1, so it's going to remain R squared minus A squared. So this is what we get when we have the point of interest lying on the negative side of the x-axis, right? On the negative side of this is left. So that would result in angle becoming 180, and when we put in, we get the potential as minus 1 over 4 pi epsilon naught times P, which is the dipole moment, divided by R square minus A square. What if I want the P to lie somewhere on the equatorial line, and we know equatorial line is the perpendicular bisector, right? So perpendicular bisector, any point on the perpendicular bisector is known as equatorial position. So if point P lies on the equatorial line, then theta is going to be 90 degrees, and if theta becomes 90, so cos 90 is 0, everything goes 0, so therefore the net potential at any point on the equatorial line would be 0. These are three situations that we get out of this result that we have derived. Extremely important, very conceptual, so take it down, go step by step and try to comprehend how we move forward with it. Well, in the next class we are going to do the numericals based on the superposition, when we have system of charges, and then we want to find the electric potential, and then we'll move with the continuous charge distribution. Because of such situations, what would be the electric potential at any point. So watch the next video, keep watching the videos, like, share and subscribe. Thank you.